So today a really beautiful problem for you. It's called disk line picking problem. Actually, it's a variant of the actual problem, but you can understand it's something about picking up lines from the disk. So without further ado, let's move ahead. So let's discuss the prerequisites for this problem. So we need to understand what do you mean by uniform sampling over geometric shape, and we need to know how to calculate the functions distribution function of random variable. We need to know the cosine law of the trigonometry, and we need to know the symmetry principle. This is one of my favorite principles of mathematics and chance. So yeah, nice bit of animation over here. So let's go to the problem. So what does the problem say? You have a disk, unit disk in R2, and you have 2 points which are randomly selected from this unit disk, uniformly selected, obviously. And we denote the d as the Euclidean distance between these 2 points, like this. We are selecting, it's nice, the GIF. And what we have to show is that we have to show that expectation of the distance square equal to 1. Now you may think that why d square, why not d? That's a question that I will attack towards the end of the presentation. So now let's do some distance calculations, how to calculate distance. Before that, let's move to the polar coordinates of the points. So r1 and θ1 is the polar coordinate when you express in terms of radius and the angle, and b is represented as r2 comma θ2. Now you know that θ1 θ2 follows uniform 0 comma 2 pi, and to calculate the distance between this distance square other, we have the cosine law at our help, and it's r1 square plus r2 square minus r1 r2 cos θ1 minus θ2. Now to understand that, we need to calculate expectation of d square, right? So we need to calculate the expectation of r1 square, r2 square, and that stuff other side. So you know the distribution of θ1 and θ2, somehow you can calculate that stuff, but what about r1 and r2? You don't know the distribution till now. So the next step is to find the distribution of r, the radius, the r1 and r2. And to do that, we need to understand the idea of uniform sampling over a geometric shape. So what is this? You have a bigger area region called S, and you are selecting a smaller region R. So the probability of selecting the smaller region is actually equal to the area of the region R by the area of total area. This is what actually the uniform sampling means. Okay, so we will take the help of this idea and move ahead to calculate the distribution of the radius. Now, the distribution of the radius, what do you think the distribution of the radius follows uniform considering the symmetry of the circle? So the natural question is asked that, does the radius of the uniformly chosen point follow a uniform 0 comma 1? No, because of the simple intuitive diagram that if you take a larger radius and take a strip around the, like, so you're trying to calculate the chance of a larger radius. So what you're essentially doing, you're taking the probability of the strip, okay, around it, a small epsilon strip, and you see that that is a larger area than the smaller strip around the smaller radius. Okay, so this using the uniform distribution over geometric shape idea, we can actually get this, that it's proportional to r square, the radius square, the area, therefore the higher probability has larger chance. So let's move to the mathematics without hand waving much, and the distribution of the radius. So we define that the area is equal to pi x square, which is the area of the radius, or area of the circle with radius x, and to get the distribution of the radius, we need to understand that the uniformly sampling over the geometric shape to get this following, that we're taking the disk of radius t and we're dividing by the actual radius, which is r equal to 1, and we get that it's equal to t square, where the radius t is between the disk of the radius of the disk is between 0 and 1, and this implies the probability density is actually 2t, where the support is between 0 and 1, right? So all of you understood this, and you can understand from that d square idea that we need to calculate the expectation of the r square. So that's why you need to calculate this, and it's just a simple integral and it's half. Okay. Nice. So we have got the distribution of the radius at our disposal, and we have got the distribution of theta 1 and theta. So we are quite armed now to attack the problem, to calculate the expectation. Now. So let's go back to the cosine law. We got this d square equal to r1 square plus r2 square minus r1 r2 cos theta 1 minus theta 2. And let's take the expectation, use the linearity of the expectation to get the following. Now comes one of my favorite part of probability, is that this you have this r1 and r2, two different, seemingly different random variables, but this is expectation gives sort of an invariance of this random variables. They're tying the knot together. They're following the same distribution, like they have the same expectation. This is really beautiful in my opinion. And using this idea, we get this expectation of r square twice minus that thing, and using the independence that r1 and r2, the radius, and theta 1 and theta 2 are independent of each other. Okay, great. So using that like the result we have derived using the distribution of r square, we get expectation of d square equal to 1 minus that quantity. Okay, this is a little bit surprising because we need to prove that, remember, we need to prove that expectation of d square equal to 1, right? So of the right hand side therefore needs to be 0. That's interesting actually. So let's investigate. So the expectation of cos theta 1 minus theta 2. Now you can understand or think, you can understand by thinking, I mean, that theta 1 and theta 2 follows the uniform, so we can actually calculate theta 1 minus theta 2, which follows triangular distribution. We can do some good integration, which I really hate and you may love, and get the result. But I will not follow that procedure. That's extremely ugly in my opinion. So let's do it in a different way. Let's try to simplify it into theta 1 and theta 2, and let's see what comes out. So we're using the cos a minus b result, and we are getting this, and we use that similar symmetry argument of that expectation, invariance argument of the expectation, and we divide over, like expectation is multiplied, distributed over the multiplication just because of the independence property, and we get this beautiful expression. Remember, it's not expectation of cos theta and sin theta wala thing, and you will get 1 essentially in that way, but it's expectation square of that cos theta. Okay, so a little bit careful approach here. So also remember that we need to prove that this is actually 0, right, to meet the expectation of the problem. So essentially each of the individual term must be 0, where theta follows uniform 0, 2 pi. Also we need to show the expectation of cos theta and sin theta is 0. So let's do that. And that's where the symmetry principle idea, the main symmetry principle idea comes in. And we need to find the expectation of cos theta where theta follows uniform 0, 2 pi, and observe the graph of cos theta. So this is a beautiful property that you can, if you think about it carefully and geometrically, due to the periodicity of cos x and sin x, you can show actually or intuitively think that this has an even probability density. Okay, just due to the symmetry of the cos theta and sin function, cos function and cosine function and sine function. And if a function is symmetric, if a random variable is symmetric and even have an even probability density, you can prove that the expectation is 0, because it will expectation under the integration sign, it will be essentially an odd function. So therefore the sum will be 0, the integration will be 0. Okay, that's a really interesting idea. But if you want to be very more mathematical and you want love to do calculations, you can calculate this and find out that the cos theta follows about is proportional to root over 1 by root over 1 minus y square. Is essentially an even probability density. Okay, so this actually proves that we have got our problem, but we will not stop here as I have promised, and there comes our food for thought. So the next question is that what will be the distribution of the distance, right? We are trying to do some variant of that, and that's an extremely explored problem of the past, and this problem actually appeared in Journal of Applied Probability or the Annals of Applied Probability in 1970s. I forgot the paper name, or the journal name, but you can search it over the net. Okay, and I've got this picture from Wolfram Alpha, and you can ask what are the expectation of the average, the mean distance between 2 points, and it comes out to be less than 1, 0.91. Why it's less than 1? That's again intuitive, because if you observe that it's first of all from geometry of the curve, like curve geometry, you can understand it's skewed towards the left and it's not symmetric, and hence it's more area on the left hand side of 1. Okay, that is the mean length, the radius length actually. Now if you try to think that why it's so, because if you randomly select 2 points, the probability of smaller length is much more probable, right? Because you're a lot of large area, smaller probability is much more. Like, I'm not talking about this very small probability, but I'm talking about general stuff. So that's for smaller probability is much more than less than one probability is much more than the more than one probability. So yeah, that's why, yeah, don't get me wrong because of the graph, but it's essentially the idea that smaller probability has a much more chance than the bigger probability. I mean, less than one and more than one. And the expectation comes in beautifully in terms of mathematical pi, but essentially it's around 0.91. You can also explore this problem. After this, people have explored a lot of generalizations of this problem in spaces where you can actually impose probability measure, and this has, like, a lot of research has been done. So we indeed dealt with a beautiful problem, and for more such beautiful problems and such videos and posts, please stay tuned to our channel. Visit our website www.cheenta.com, and please do like, share, and subscribe. Good night. Until then, stay tuned and stay blessed.